Hello, we are going to go through my model of a GC. So we start off with the dark green needle, and that contains the analyte, and it injects the analyte into the orange injection port. And this port is heated in order to get the analyte into the gas phase quickly. We're using a splitless injection port, which has a closed valve and a lowered gas flow. This is a good method when you have high volumes and low concentrations. And we lower our gas so that the injection flow rate is the same as the column flow rate. And this method gets about 80% of the sample into the column, which is a good margin. And it also uses solvent trapping to help increase resolution. And what we do is, since the injection port is heated to get the analyte into the gas phase, we hold this area right before the column starts at a temperature that's just below the boiling point of the solvent. So we get some condensation right here, and that actually helps minimize the head start effect. Now we keep our entire oven heated as well, but we keep it heated at a lower temperature than the injection port, because here we're trying to get the molecules into the gas phase, and here we're just trying to maintain the gas phase for those molecules. We're using a polar column because we're testing 3 polar compounds, and since they're like with like, they will interact with a polar column more than they would with a nonpolar column. And we're using temperature programming so that the beginning will start off with the beginning temperature, and it gradually increases until we reach the final temperature. This means that since it's a polar column and all of the molecules are polar, they'll come off based on their boiling point as they go from the stationary phase to the mobile phase. And once our analytes are leaving the column, they go into this red bit, which is our flame ionization detector. And that detector uses a hydrogen flame to burn the compounds that come off of the column, which produces ions. And these ions cause a change in the resistance of the system, and the intensity and just sheer number will hit a detector plate, and the information of the resistance change will be sent to the computer, where the intensity and area can be quantified. So we'll be able to tell that our analytes have a specific area, and this is the quantification method. Now, since we're testing 3 polar compounds, which are methanol, ethanol, and butanol, they're going to come off of the polar column from lowest boiling point to highest boiling point. So methanol will come off first with a 65-degree boiling point. Ethanol will come off second with a 78-degree Celsius boiling point. And lastly, butanol with 118 degrees Celsius. Now, the whole method is good because we're using flame ionization, which is great for organic molecules and has a great sensitivity and dynamic range. But it does have the problem that since you're having to maintain the flame as well as deal with incoming gases from other parts of the system, you need an instrument that has multiple gases that's going to be able to maintain the hydrogen flame as well as air, nitrogen, whatever gases your system requires. And you have to be able to buy all of those gases separately. And we're utilizing an injection port, which, as previously stated, is good for high volumes, low concentration. You can use some solvent trapping, and that will help with organic molecules as well, because it helps with most molecules. And that is my model.